What does it take to go from zero to superhuman? That's the question I want to explore in this series. I am Sander, and I'm going to be documenting my journey as I learn to build AI and other systems that can outperform humans. To begin our adventure, we need a perfect sandbox, something simple enough to understand but complex enough to challenge us. That's why, in this first episode, we're tackling Tic-Tac-Toe. The goal is to build an unbeatable bot for the classic game played on a 3x3, as well as on larger board sizes and with different win lengths. And I'm excited to start, and I hope you are too. Let's quickly cover the basics of Tic-Tac-Toe. The game is typically played on a 3x3 grid with two players. Each player chooses a symbol, usually X and O. Players take turns placing their symbol in any empty cell on the grid. The objective is straightforward, to be the first to get 3 of your symbols next to each other, which you can achieve diagonally from corner to corner, vertically down any column, or horizontally down any row. Now we need to make a digital version of Tic-Tac-Toe so we can play against our AI. For that, we'll use a graphical user interface library called tkinter. First, we define a class called Tic-Tac-Toe and initialize our window. We give it a title and define its geometry, which is the size of our window. Next, we will define how we will keep track of the game state. We use self_board equals empty string 9 times, giving us 9 empty positions representing our tic-tac-toe board. We also set a current player that randomly starts as either X or O. Now we need to create the actual playing board with the createBoard function. Here we use a nested loop where we create 9 buttons with empty text and add them all into a 3x3 grid using button.grid. These buttons also have a built-in function called makeMove that is triggered when clicked. When we make a move, we change the text of the button to show the current player's symbol, so either X or O. Finally, after every move, we check whether the game has ended. This can be because there is a winner or the board is full, leading to a tie. Either of these will trigger a pop-up message like this. If the game isn't over, we switch players by updating self.currentPlayer. Okay, so finally I've made some small additions to the graphical user interface. I've added a new game button that resets the board, and I also added a scoreboard that keeps track of the score, as you see here, and can easily be reset. And finally, a player selection feature so we can select against which bot we can play and also even let different bots play against each other. So let's now move on to the first AI system we are going to implement, the expert system. This is actually the oldest form of artificial intelligence and was heavily developed in the 1960s and 70s. I'll quickly explain how it works. It's basically just a simple rule-based system. So what we do is we give the AI a set of if-then rules. The system takes the current game state and processes it through the rules knowledge we've programmed into it, and then outputs the best move according to those rules. The AI just goes through these rules in order and picks the first one that applies to the current situation. The performance heavily relies on which rules we decide to put into the system. Thus the system relies on expert knowledge. That is why it is called the expert system. Alright, so now let's build our expert system. I'm going to implement it with some very simple rules. So the first rule, if the middle is available, let's take it, because the middle is a strategic position as it gives the most winning lines. The second rule, let's take a corner if it is available, since corners are the second best spot because they're also part of the 3 winning lines, just like the center. And the third rule, if we can make a winning move, let's definitely take it. The fourth rule, we block our opponent's winning move because we don't want them to beat us on their next turn. And finally, if none of these rules apply, well, let's just pick a random position. So this is what it looks like in code. We start off by defining a base class called bot, which has a make move function that all our bots will inherit. We then define a subclass called rule-based-bot, where in the make-move function we implement the rule logic we just discussed. One thing that I did change is the order of the rules to make them more logical. So instead of taking the center first, we prioritize making a winning move when it's possible, because winning should always be our top priority. Finding the winning move is also quite straightforward. We just look through all the winning patterns to see if we have two of our simples and one empty position. If that's the case, the move we should make is that empty position. The same logic applies for blocking an opponent's winning move. Alright, so let's see how good our expert system is and if we can still beat it. I expect it to be quite good, but still have some room for improvement. Let's see. That's a tie. I think I lost here. Yep. So I'll be honest, I think I made a mistake here, but it's really hard to beat. And the question is, what does this make me? Does it make me an expert by programming good rules and losing against my own bot? Or am I a sucker for losing against a simple program like this? I'll leave I'll leave that up to you. But I have no idea if this is playing optimal already with only these simple 5 rules, so it would be maybe interesting to see if we can maybe make a better bot and if that bot can win against this one. So let's do that. The main limitation of our current bot is that it cannot plan its moves ahead. It only decides where to move based on the current board position. Maybe there are some strategies where we can fool it by thinking multiple moves ahead. For this, we can use the minimax algorithm. Here is how it works. We have two players called Min and Max. Max wants to maximize the score, Min wants to minimize it. If Min wins, the board score is -1. If it is a tie, it is 0. And if Max wins, it is +1. Starting from any board position, let's say it's Max's turn, the algorithm explores every possible move Max can take. Then for each of these moves, it explores every possible response Min can take. This continues back and forth until we reach a game ending. Either someone wins or it's a tie. This creates what we call a game tree, where each endpoint represents a final game state. Now here's the clever part. To decide which move is best, we work backwards from these endpoints. If it's Max's turn at any point in the tree, Max will choose the move that gives the highest score, because Max wants to win. If it's Min's turn, Min chooses the move with the lowest score, because Min wants Max to lose. The algorithm assumes both players play perfectly. So if we work backwards from the ends of the middle branch, we started very simple, where each parent only has one child state. So their Min and Max is just the value of their only child. Then one state further up, there are two possible child states and Min is the player to make the move here. So if Min chooses optimally, it will choose for the branch that led to 0, making the score of this branch also 0, as the minimum of 0 and +1 is 0. You can try the final branch for yourself to see if you understand the principle. Now that we worked our way back up to the root of the tree and scored all branches, we can easily find the best move for Max by simply choosing the branch with the highest score. The minimax algorithm guarantees that we are making the mathematically most optimal move. This is how it looks in code. The minimax function works recursively. It calls itself over and over to explore the game tree. First, we do our terminal checks. Then we loop through all empty positions on the board, make that move, and recursively call minimax again with the opponent as the current player. If it's our turn, we only keep scores that are higher than our current best. If it's the opponent's turn, we are minimizing, we only keep scores that are lower than the current best. This is basically dynamic programming. We're building up the solution by solving smaller sub-problems and combining the results. Let's see if our minimax bot can beat the rule-based bot. For this, I wrote a script that doesn't rely on the graphical user interface and that can quickly simulate multiple games. Here we'll simulate 100 matches, and it looks like they tied 100% of the time. This means that our simple rule-based system was already playing optimally and is actually impossible to beat. So this means that for simple 3x3 tic-tac-toe, we've already built a superhuman system that's completely unbeatable by only programming 5 simple rules. But why stop here? Let's be honest, 3x3 tic-tac-toe is quite boring. So let's see if our bots can still work on larger board sizes with longer win lengths. This is where things could get really interesting. But in order to work, we first need to change our code so that we can configure the board size and the win length. Then we also need a function that automatically generates all winning positions based on the board size and win length. Okay, so we're currently playing on a 4x4 grid against our rule-based bot, and the win length is 4. So let's see if we can beat it. The thing is with this bot is that we already know which moves it is going to take. It is always going to take the corners if there's no center available, and a 4x4 grid doesn't have a center. So it's gonna start out by taking the corners. So we have the freedom of 4 moves to create a trap like this, and this allows us to win automatically. This almost works always, as you see here. So this is clear that our rule-based system was really good at 3x3 tic-tac-toe, but applying the same rules to a 4x4 really has its limitations. Let's now see how our minimax algorithm does. The game crashed, and that was actually as expected, as I'll explain now. The issue is with the recursive tree search. As the board size increases, there are exponentially more games that can be played, making the tree both deeper and wider. For 3x3 tic-tac-toe, there are about 255,000 possible games, which is totally manageable on most computers. But jump to 4x4 and we're looking at over 20 trillion possible games. And for 5x5, we're talking about nearly 15.5 septillion possible games. Even the most powerful computers cannot search a tree that massive, so we need to make this more computationally feasible. The simplest change we can make is limit the search depth of our tree. So instead of planning all moves ahead, we only plan a few. Like here, just 3 moves deep. But this won't be without a loss in performance, because now we're taking decisions based on incomplete information. We might miss a brilliant winning combination that's 5 moves away, or walk into a trap that would have been seen if we had looked deeper. But it's a necessary trade-off. We sacrifice perfect play for computational feasibility. This is how we modify the original minimax function. We just add a depth counter and exit the recursive loop when we surpass the maximum depth. But as I mentioned, limiting the search depth hurts our performance, since we're no longer relying on complete information. However, there's actually a clever technique that lets us avoid exploring the entire tree while still maintaining perfect play. This technique works as follows. So let's say we first explored this branch, and through our backpropagation we know that this node has a board score of +1, which is the highest score possible. The question becomes, do we still need to explore the other branch to determine the board score for the parent node? Actually no, because +1 is the maximum possible score, so Max will definitely choose +1 without needing to know the value of the other child node. So this entire branch doesn't need to be explored anymore, and it can be pruned. Now we explore the other branches. The first value is 0, so we still have to explore the other branch to see if it has a higher score. Now we can score the entire branch. Then for the next branch, we first explore this sub-branch, leading to these values. But again, do we need to explore this complete sub-branch to know what the best move will be? Min is the player here and will surely choose a value smaller than or equal to -1, but -1 is already the lowest possible score, so we're certain Min will choose -1, so this entire sub-branch can be pruned as well. We explored much less of the tree and still found the best move. This technique is called alpha-beta pruning, where alpha stores the best move for Max and beta stores the best move for Min. Here's the code implementation of alpha-beta pruning. We add 2 parameters, alpha and beta. After each recursive call, we update alpha or beta depending on whose turn it is. Both stop if they found a maximal and minimal score respectively, and prune the remaining branches. Additionally, if beta becomes less or equal to alpha, we break out of the loop, pruning the remaining branches. These optimizations allow Minimax to work on a 4x4 grid, but with a trade-off. We can only look 4 moves ahead into the future, and with alpha-beta pruning, this becomes 7 moves. The attentive viewer would think, hey, as the game progresses, why do we still use the same search depth? And you would be very right to question this, because the tree should become more narrow as the game progresses, lowering computational demand in the process, which in theory would allow us to search deeper in the later stages of the game. We can solve this with iterative deepening. Here, we're going to explore the tree in a particular way. We'll set a time limit for exploring the tree, here 5 seconds. We'll start out with the maximum depth of 1, and after searching at this depth, we check if we still have time left. And if we do, we search at depth 2. And then again, if there's still time remaining, we search at depth 3, and so on. And you see at the beginning of depth 4, we run out of time. So we exit the tree search and use the result from the deepest depth we were able to explore completely, being depth 3, which results in a move to the right node. The code implementation is quite straightforward. We start our timer with the time function from the time library and then begin with the search at depth 1. And before calling minimax, we check if we haven't surpassed our search time yet and also have enough margin to go for another round of recursive search. Then we call minimax. Within the recursive minimax loop, we also check at every node whether we have surpassed our search time before we call minimax again on the next node. And as you see, this allows us to search deeper in later stages of the game. The benefits are even further amplified when combined with alpha-beta pruning. But we're not done optimizing yet. There's another clever technique we can use to go even deeper, called transposition tables. Let me show you how this works. Here's a game state. Now, this board can be created by different game sequences. Look at the possible orders in which the X's and the O's can be placed to generate the same board position. These are called transpositions. This means this exact board will occur in many different branches of the game tree when exploring from earlier positions. Also, since these boards all have the same game tree, it's redundant to compute them separately at every occurrence. And we can explore the tree once and store the value of that position in a transposition table. Then, when we come across another instance of this board, we can simply look up what the board value will be instead of exploring all its children and doing backpropagation all over again. Now let's look at the code. For this feature, we use a dictionary to store the transpositions. Before each move, we clear it to prevent memory overload. Then we call minimax. First, we generate a hash for this board position. This is simply a tuple of the game state. Then we check if the current board position is already present in the lookup table. If this is the case, we can retrieve the best move and score directly. If not, we recursively call minimax and perform the search as usual. Then, after our search is complete, we store the best move and best score of that node in the transposition table. This way, if we encounter this board position again, we can do a quick lookup. And when we combine it with alpha-beta pruning and iterative deepening, we can in fact go even deeper. Okay, oof. It was a lot of theory and a lot of coding, but it actually paid off. We are currently playing against our minimax bot on an 8x8 grid, and I haven't been able to beat it yet. However, it very often takes the top left position, and I think I know why this is, and it's because of our board scoring function. If the tree search does not find a terminal position, then all branches have a score of 0, and it will just take the first move it explored, being the top left move, because we explored the tree from left to right. So this makes the bot very easy not to lose against, but very hard to win against. However, for more strategic variants, like requiring a win length of 4 on a 5x5 grid, it is actually pretty bad. And to be good at these kind of game variants, you really need a way to evaluate which non-terminal position is better than the other. So we need a way to score them differently and assign higher scores to better positions. For this, we could write a function to score board positions based on factors like open-ended 2 in a row or 3 in a row formations as shown here. However, as you saw with our rule-based system, such handwritten rules don't really translate well across different board sizes and win lengths. But actually, we can let the game itself tell us how good a position is by simply simulating a random game from this position and then seeing if this resulted in a win or not. And we can do this random simulation many different times. Then we can do the same for another board position. And through these random simulations, if one position results more often in a win than any other position, it is probably the best one. Also, the nice thing about statistics is that we don't have to change anything if we change our grid size or win length. So now our opponent makes his move, and then again we score every next board positions by doing many random simulations, and from that information we can select the best move. This statistical approach to board evaluation forms the foundation of Monte Carlo Tree Search. Now that you understand how we score positions, the rest of the algorithm becomes quite straightforward, but still remains very elegantly designed. So let's start from an empty board position where it's O's turn to play. Monte Carlo Tree Search works by repeating three key steps many times: selection, expansion, and simulation. Expansion creates a new child node in the search tree by adding one unexplored move from the current position. Then simulation plays out a complete random game from the newly expanded position to determine who wins. As we perform these simulations, we keep track of some important statistics, of which one is node visits. This counts how many times we did a simulation starting from that position or starting from one of its children, while wins tracks how many times of those simulations resulted in victory for us. Next is the selection step. This step only becomes relevant once we've fully explored a certain depth of the tree, so we can skip it for now. Instead, we'll continue with the expansion and simulation steps. We add another unexplored move, then run a random simulation. We repeat this process until we've explored all possible moves from the first depth level. Now we can finally introduce the selection step. Selection determines which promising path to explore deeper when we have multiple options available. Selection must balance two competing priorities: exploitation, which refers to choosing moves that have performed well so far, versus exploration, which refers to trying moves we haven't tested much yet. This balance is crucial for finding the optimal play efficiently. And to achieve this balance, Monte Carlo Tree Search uses the upper confidence bound for trees, short the UCT formula. UCT calculates a score for each possible move that combines both its current win rate and how much we explored it. In our example, each node now has only one visit, and one only resulted in a win, which was the center move, and the highest UTC score is the center move, so this one will be selected. Selection is performed at every depth level where expansion is no longer possible, but as soon as we reach a level where we can add an unexplored node, we switch to expansion and then simulation. After simulation, we update the statistics of the node we just explored and propagate these results up to all its parent nodes. Then we perform selection again, but now based on the updated node visits and wins, which can result in expanding and simulating a different part of the tree, as is the case here. This loop of selection, expansion, and simulation can be repeated thousands of times for each move, building a large search tree. The move with the most visits becomes our estimate of the optimal move. Now you should have a really good idea of how Monte Carlo Tree Search works. The code implementation is quite extensive, so I won't walk through it. However, everything is open source on GitHub, so check it out via the link in the description. Okay, time to put our Monte Carlo Tree Search bot to the test, and let's do that on a 5x5 grid with a win length of 4, which is a more strategic variant of the Tic-Tac-Toe game where our previous bot really struggled with. And our bot still has a thinking time of 5 seconds, in where it will do many iterations of selection, expansion, and simulation. So let's see who can win. Let's do the first to reach 5 points wins. First one is a tie. Here's my first loss. I didn't see that one. It's not going great, to be honest. One mistake and you're done. Ha! With my starter advantage, I found a way to automatically win here. We're coming back. Guess not. Okay, final point. It's over. Sooner or later, I make a mistake and then I'm directly punished for it. The thing clearly plays optimal and you cannot win from it. Only in rare occasions where you're able to start and you find a perfect sequence that automatically results in a win and isn't defendable. So it's clear our bot is really good, and yeah, let's see if it also works on different grid sizes. Here we're playing on a 10 by 10 with the win length of 10, and it seems to be still unbeatable here. It's already blocking all my winning lines, and it is coming up with a very unique strategy. Okay, there's no point playing further because it's certainly gonna end up in a draw. But finally, does it still work as good on the 3 by 3 grid as well? And the answer is yes. Let's take a moment to reflect on our journey. We started with a very simple rule-based system which surprisingly was very strong at 3 by 3 tic-tac-toe but lacked generalizability when the game rules changed. Then we explored a more complex algorithm like minimax so our AI could plan in the future, which after some optimizations worked quite well on larger board sizes as well, but played very defensively. Then finally we explored Monte Carlo Tree Search, which works exceptionally well on all kinds of different variants of the original tic-tac-toe game, to the point where it's almost unbeatable except for some specific opening sequences. So I think it's fair to say we've built a superhuman tic-tac-toe AI. And I am very excited to use what we've learned in this project to tackle more complex and perhaps fun projects, like making a Go engine or a chess engine. If you'd like to test yourself against the AI systems we've built, head over to my website. Just make sure to spell my name with the Y, otherwise you'll end up on someone else's website. Once on my website, find the Tic-Tac-Toe project card. And here you can select all bots or customize the grid size and win conditions. I really want you to experience firsthand the journey we've taken and see each bot's unique strengths and weaknesses. If you've enjoyed the video and want to be around for the next project, please drop a like and subscribe to the channel if you feel like I've earned it. Thank you for watching and see you later.